Hey, welcome back to the last section, if you will, of this particular lecture. Why is this important? Well, it's important already because now we are able to take a basic weather map and forecast wind speed and wind direction, which is kind of cool. But there's another twist to this, which makes it really interesting, because it also enables us now to figure out the major wind systems of the planet. Because it turns out, it's kind of shown schematically in this diagram, wind direction on Earth is not random. Depending on where you live, you have a very dominant wind direction. So for us, for example, in the mid-latitudes in North America, wind generally comes from the west. If you live in the tropics, if you live, for example, in Brazil, or if you live in Hawaii, it's the other way around. Winds always come from the east. The point being is, wind direction on Earth, on planet Earth, is not random, but rather very much predictable. And we can do that now. Here's the basic sequence, right? Air pressure differences, horizontal air pressure differences, cause wind. Wind brings us weather, and if we take weather and average it over, say, 30 years, we can define climate. And there's two types, if you will, of air pressure variations. First of all are sort of the short-term ones. Localized air pressure variations, maybe regional air pressure variations, temporary air pressure variations. These give us local, regional winds and local and regional weather. However, it turns out that we also have long-term, large-scale, sort of almost permanent air pressure systems on Earth. And those define the global winds and the global climate. So that's kind of cool to think about. It all depends on air pressure differences, locations of high pressure systems, locations of low pressure systems. Short-term variations in that give us wind at the local scale, but there's also these almost permanent high pressure areas on the planet, these almost permanent low pressure areas on the planet. And that gives us global wind and global climate. Let's look into that. Here's two weather maps. This happens to be the 10th of November. This happens to be the 12th of November. Atmosphere is extremely dynamic. So air pressure patterns change from minute to minute, hour to hour, day to day, right? Week to week. So the location and the strength of these high pressure areas that you can see here, of the low pressure areas, changes constantly. These are just snapshots at a specific time, 11:52, 12:58, right? And that kind of makes sense when you think about it. Because differences in air pressure give us wind. But if you think about winds, the winds also ultimately try to even out these imbalances in air pressure by moving air from high pressure areas to low pressure areas. Right? So on a map like this, you can say, well, okay, here's a pressure hill, here's a pressure hole. That gives us a pressure gradient, and air is going to flow from high pressure to low pressure. But as it does so, it's going to reduce the high pressure area here and increase the pressure here. So you have an incredibly dynamic situation going on, where air pressure and differences in air pressure create wind, but at the same time, the wind moves air to even out these air pressure differences. That's kind of cool. However, we also have literally large, almost permanent high pressure and low pressure systems on Earth. And they're kind of shown on this map, which is figure 5 5-16 from your book. Right? There always tends to be a high pressure area here. There always tends to be a high pressure area here. And these high pressure areas and these low pressure areas are, change in size. They get a little bit stronger, they get a little bit weaker, but they're always around. That's why they even have names. For example, this high pressure area here is called the Azores High. This low pressure area is the Icelandic Low. This high pressure area here is the Siberian High. So we have these almost permanent pressure systems on the planet, these almost permanent high pressure areas, low pressure areas. That gives us climate. And then superimposed on these large scale systems, we have local scale and regional scale systems, such as Hurricane Sandy, such as any old storm, if you will, right? So, if we have air pressure patterns that are very much constant, low pressure areas, high pressure areas, then what does that mean? It means that you get consistent large-scale atmospheric circulation patterns, which is basically a fancy way of saying wind direction on Earth is not random. Because if these pressure systems kind of hang out where they are all the time, then you always kind of have high pressure, low pressure, and a pressure gradient that sets the air in motion. And that's exactly what's going on. Because we have stable, large-scale air pressure patterns, we have stable, large-scale wind patterns. For example, where we live in the mid-latitudes, we have the westerlies. Winds blow from California to Massachusetts. They blow from the west to the east. If you live in the equatorial regions, if you live in the tropics, you have the trade winds. The trade winds blow from east to west, from Africa to America, for example. That's the big story here. So, what we've developed here is the basic rules that control wind speed and wind direction. Pressure gradient force, Coriolis force, friction force. We put this all together and now we can predict wind speed and wind direction. Why is that important? Because that also explains the fundamental global atmospheric circulation, the fundamental global wind patterns that we'll talk about on Monday the 19th and then Wednesday the 21st. Right? So that's the wind story, the pressure and wind story. Make sure you complete the worksheet for today, and that's the end. And I'll actually see you in person again on the 19th, on Monday the 19th. So thanks for watching.